In this video, we're going to look at the linear approximation. And so, what a linear approximation is it's basically using a tangent line to approximate a function. The tangent line that we're going to go through will be go through what we're going to call the center, which is going to be x naught f of x naught. And for the most part, in general, so long as we have x's near x naught, the approximation will be close. The closer we are, the closer the approximation. In general, the farther we are, the worse, or the less we can trust this approximation. Now, I don't usually memorize this formula, but it is worth realizing, because it extends up to quadratic and further approximations, that the linear approximation, or linearization, L of x, will equal the tangent line. So we have the derivative evaluated at x naught times x minus that x coordinate plus the y coordinate, so f of x naught. So let's see an example of this straight away. I want to find the equation line tangent to f of x equals root x, centered at 9, and then use that tangent line to estimate the value of f of 9.1. And so what I'm going to do is, just like any other tangent line, I will find the point. And the point is, of course, found by evaluating f of 9. Square root of 9 is 3. So we have the point, 9, 3. Next, I need the slope. I'll get the slope by evaluating the derivative. So f prime of x will be 1 over 2 root x. And I evaluate that at 9 as well. So f prime of 9 will be 1 over 2 root 9, which is 1/6. This will give me my tangent line, or my linearization, centered at 9. L of x is equal to 1 over 6 x minus 9 plus 3. And now I can use it to estimate this value by saying, okay, 9.1 is close to 9, so f of 9.1 must be close to L of 9.1, which is equal to 1/6 9.1 minus 9 plus 3. And every time I'm doing this linearization or linear approximation, this will end up being sort of the delta x, the change in x, how far my x value I'm trying to find is from my center. So this will be 1/6 times 0.1 plus 3. 0.1 is 1/10, so this will be 1 over 60 plus 3. 3 is the same thing as 180 over 60, so this will be 181 over 60. And that is my approximation for the square root of 9.1. Before we go on to see some about error, let's look at graphically what happened. So here is my graph of the square root of x. And we're going through this point here at 9, 3. And you can see the tangent line, as long as I'm very close to 9, the black line and the green curve are very close to each other. But as I move further away from 9, you see that the black line gets further off of the green curve, making it a worse approximation. So that's the idea of the closer the center is to the point I'm looking for, generally the better the approximation is. There are, of course, exceptions where the curve might come back and get close to the line again, but in general, that's the case. All right, so now error. And first thing to say is error is not a bad thing. Error is just some measure of how far the approximate value is from the actual value. And in the real world, for continuous measures such as height, time, volume, mass, pretty much everything is going to have error in it because I can't know exactly how long a pencil is or exactly the volume of a glass of water because I don't know exactly where all the atoms are. You can go into like Heisenberg's uncertainty principle saying there are things that I just can't know exactly. So error is not a bad thing. Generally, having less error is better than having more error, but error will be there in real world situations with continuous values, as opposed to discrete values. I can count there are 10 students in this class, not 10.1 or 9.9, but for continuous values, there will be error. And we're going to talk about 3 different types of error. So the first one is absolute error. And this is just strictly how far the two values are apart. So it's the absolute value of the actual minus the approximate. And again, in general, lower errors are better than higher errors, but the absolute error leaves something out of the equation. For instance, if I wanted to measure a pencil and my measurement was off by 1 inch, that's pretty bad because pencils are usually maybe 5-6 inches long. If I wanted to measure the diameter of the Earth and I were off by 2 inches, that's pretty good because the Earth is a few thousand miles across. So while we might think that 2 inches is always worse than 1 inch for an error, it really depends on what I'm measuring. And so a way to account for that is something called relative error. And the relative error is basically the error divided by the actual value. And I prefer this as a way to look at things because I'm used to seeing, 0.5 meaning half, 0.2 meaning 1/5, and that type of thing. But some people prefer percent, so percent error is basically just taking the relative error and converting it into a percent by multiplying by 100%. And so this is error. Now let's talk about one more thing, which is the idea of are we under or above it? So an underestimate or an overestimate. And what makes linearizations or linear approximations be different from the actual value is the function can be curved. And here's the trick to it. So my line is straight. If my curve is concave up everywhere or everywhere between the center and the value I'm looking for, so the second derivative greater than 0, then I'll be an underestimate. If my second derivative is less than 0, if I'm concave down, you can see the actual function is below the linear approximation, then I will have an overestimate. So let's see an example of all this stuff. Use a linear approximation to estimate the value of the natural log of 0.9. Next, determine whether this estimate is an overestimate or underestimate. And calculate, let me put that in there, calculate the absolute, relative, and percent error. So, here we go. When I see this, I think, okay, my function is going to be the natural log function. My center is going to be at 1, 0. I chose 1 because it's close to 0.9, and I know that the natural log of 1 is 0. I need to find the slope to get the linear approximation. So f prime of x, the derivative of natural log is 1 over x. F prime of 1 is 1 over 1, which is 1. So my linear approximation will basically be L of x equals 1x. 1x minus 1, or x minus 1. Okay, next up, I'm going to use this to estimate the natural log of 0.9. So since 0.9 is close to 1, then this will be approximately L of 0.9. And L of 0.9 is 0.9 minus 1, which is about negative 0.1. Next, overestimate or underestimate. So I'll look at the second derivative. So the second derivative of x will be the derivative with respect to x of 1 over x. If I want to avoid using quotient rule, which I don't want to actually have to use quotient rule, I'll look at this as the derivative with respect to x of x to the negative first power. And now I can just use the power rule, which means that's going to be negative 1 x to the negative second. And I can just evaluate it from here, so the second derivative evaluated at 1 will be negative 1. Since this is negative, we know that we're concave down, which means that my line will be above the curve, so we have an overestimate. Now, some work on errors. So, to find the absolute error, I basically just take the magnitude of my approximation, negative 0.1, minus my actual. And my actual is going to be the natural log of 0.9. And for this, I'm going to use the calculator. Let me close off that absolute value. So go to the calculator, and I will find negative 0.1 minus natural log of 0.9. I get 0.00536. To get the relative error, and I guess I should have included this in the previous slide. Let me go back and put that in here. All of my errors should be positive, so I want to make sure that this remains positive as well. So with the relative error, I take this, 0.00536, divided by the natural log of 0.9, and do the absolute value, because this natural log will be 0. So let me go to my calculator and do that. So divided by the natural log of 0.9, and I'll just drop the negative sign, so I get 0.0509. And then finally, to change this to a percent error, I just multiply this by 100 and write the percent after this. So this will be approximately 5.09% off. All right, I hope this helped out. Feel free to comment below if you do have any questions.